All right, so today I'm going to be covering the practice exam, or rather reviewing for the final exam. Okay. So let's go ahead and get started with that. Okay. GitHub. Okay. So share screen. Screen one. All right, everybody. Let's go ahead and I'm going to go to Classroom. And I'm going to go to Destruct, where all my code is. And then I'm going to go to this studyguide.pdf. I'm going to download it. And there's links there at the bottom. So this is first off a final exam guide that I wrote a number of years ago that simply covers the topics. You can find it on my GitHub in the Classroom. Programming topics, things you should know for the final exam. And then here I have links to other courses that have done final exams. So let's see. So today we're going to start out with the Harvard Data Structures final exam. Oh, and before I continue any further, updates. Many of you have asked if I teach a course, any courses after this. And I normally say no, but it just so happens that I've been asked to teach 3223 in the spring. So that's data structures and algorithms. I haven't taught that course before. I'm filling in for another professor as an overload. So it's going to be an additional course on my part. It will be Tuesday to Thursday, from what I understand. Sorry, Tuesday and Thursdays from, let's see what time. From, let's see, my class is going to be right before my other class. So 1 second. I just want to double check the time. This is for data structures and algorithms. So the class that immediately is coming after this in terms of like what you have to take. So it would be from like 12. I think it would be at 12:30 would be the time. 12:30 to 1:50 twice a week. So if that interests you, you should probably sign up.
I don't, but I went on the registration thing. It didn't appear there though. It was just Professor Hughes and another class. But
right, I'll probably be covering another class. This is something I only spoke about over the weekend. It still probably has to update.
So, do you have any idea when it will be available? Because registration date is very close.
I don't know. I don't handle registration or any of that stuff. Let me see. So TU Portal. So first off, let me see if I've got any of my courses. Let me see if that's even percolated for the spring yet. Yeah, I don't even have it on my schedule yet. So this is only what I've been told. So I still have to, let's see. Course catalog, class schedule. Let's see, 20. Okay. Computer and information sciences. Come on. You can do it. $21. Okay. So 3223. Let's see. There it was. 3223. So that was not the page to look for. This is the page to look for. But we'll take a minute to, here. Yes, so I'll most likely be covering this section over here. This class over here. I'll be taking over as the professor for it, as opposed to Hong Chang Gao, who is being moved to cover a different class.
I see everything.
So keep that in mind. All right. Otherwise, Professor Hughes is excellent. I'm going to be taking all my cues from him. So, you know. Okay. So this is the the way I like to review for my practice exams or for my exams is I like to use the practice exams from other schools. Unplug you. Hold on a second. Hopefully I have the Wacom tablet set up. Doubt it. No, I doubt it. I won't really be able to use this sucker at all. That stinks. Really? It's set up and ready to go? Are you sure about that? Yeah, I'm not getting it. All right. So anyway, this is a bunch of data structures questions. It is really a pretty thorough exam. Okay, let me just download my drivers for this and I'll continue. Sorry, thought I had it set up, but it did some more upgrades while during the break. Accept, installing. All right, so let's look at the first question. So suppose we have items A, B, C, D, and E pushed in that order onto an initially empty stack. There we go. That should be able to work. So then S is popped 4 times. As each item is popped off, it is inserted into an initially empty queue. Okay. So if 2 items are then removed from the queue, what is the next item that will be removed from the queue? So what is the answer to this one? So let's go ahead and see. We've got, suppose A, B, C, D, and E are pushed into that order into a stack, a badly drawn stack that's initially empty. Then we pop this 4 times, and each item, as we pop it off, is put into a queue. So let's go ahead and draw our queue over here, which is going to go this way. So E, D, C, B, right? Stacks are first in, last out, and queues are the opposite, which is for first in, first out. So we've dequeued those items. A is the only thing left in the stack, or we've popped those 4 items. They're the only things left in the stack. Every item is popped off. I don't need these headphones. It is inserted into initially empty queue. If 2 items are then removed from the queue, what is the next item that will be removed? So we need to remove 2 items from the queue. Would help if I was trying to write with the right side. Move 2 items from the queue. So the next item in the queue would be C. Make sense? Clear all drawings. Next question. All right. If the binary tree below is produced in, so let's say we're trying to do a pre-order, if the binary tree below is pre-order, printed in pre-order traversal, what will the result be? So here we've got 6, 17, 22, 9, 4, 16, 12. So to do pre-order, we do what node first? What's first in pre-order traversal? Let's see.
The root or the parent?
Yeah, the root. The root is first. So we do 6. So 6 has to be first. So that means it can't be an A or B. That means though that, so let's go ahead. So it's handle myself, then handle my left subtree, then handle my right subtree. So handle my right, and we got to handle my entire left subtree, which is 3 items before handling this side. So it can't be D because D is 6, 17, 22, 9, 4, 16, 12, which if you think about it, actually, it's breadth first search. That's what D is. It's breadth first search. It's doing this, 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 this. Myself, then my 1 steps away, then my 2 steps away. That is, in terms of trees, sometimes called level order traversal. Okay, C. Let's look at C. C is 6 and then 9. So handle myself first, then do my left subtree. 17 should be handle myself first, then handle my, but that's not what happened there. So no, it's 6, 17, 6, 9, 17, 4. It's really weird. Then 12, 20, then 16, 22, 12. So 6 goes first, then I handle my left subtree, which says, hey, 17, handle your left handle yourself, then handle your left subtree, then handle your right subtree. Then we go to 22, who says, hey, I'm going to handle myself, handle my left subtree, handle my right subtree. So the answer there is E. Makes sense to everybody? All right, I really like this question over here because it talks about it's basically the graph version of Arraylist versus linked lists. All right, so a graph implementation that uses a 2-dimensional array to represent edges would be the most reasonable in which of the following cases. So notice that we have E, since a graph can only be represented as a linked structure. So we have 2 ways of representing graphs internally, right? Right, there's 2 different ways we can represent graphs. One is a linked structure. So basically you have a linked list and say A has a connection, has an edge between B, C, and D. B has a connection to A and C. C has a connection to A and B, and D only has a connection to A. Right? That's one way to do it. Another way to do it is to have an array, right? And it's basically a matrix where basically we have A, B, C, D over here, and then A, B, C, D over here. Not going to do the same one because I can't remember really what I just did there. But we have this and a very poorly drawn C over there. Okay, and so 0 over here mean it takes no cost to get from myself to myself. And basically here, what I can say is, hey, if there's a to get from A to B, maybe cost 3 units of cost, and get to B to A costs 1 unit, right? So you can represent directional edges this way. Okay, so question is, when do you want to use one type versus another? Anybody remember what when we want to use one type of array versus another is?
When you try to find shortest path, I don't know. No.
I did cover it in the videos.
It was, I don't remember exactly, but it had to do with a sparse graph versus a non-sparse graph.
Yes, it had to do with sparse versus dense graphs. So the idea here is that which is more they both have basically an overhead cost, right, associated with them. A linked list, right? The memory costs for the links, right? Just like in a normal linked list, right? Or in a hash, or if you're using a hash table, right? It's got to keep that empty space, right? Available. And since it's doing bucket chaining, then again, linked list. Hold on, I've got a stink bug right here that I just want to let outside. Okay. So on the other hand, with a 2D array using for a linked list, right, we use the cross section to represent, whether there's an edge there. But if we don't have a lot of edges in that, then you get in a lot of empty spaces. You can waste some space that way. So linked lists are better for, so the linked format is better for sparse graphs because that uses less information. But as it gets more dense, that overhead starts to make less sense for the an array-based graph. Or sorry, that as it gets more dense, it starts to make less sense for a linked structure, and it starts to make more sense to use an array structure. And so the array structure is really great for those dense graphs where you have a lot of edges, because a lot of those spaces are going to be filled. And so the magical cutoff point that our book recommends is if 25% of all possible edges exist. So, right, if you've got n squared possible edges, right, where you have n nodes and there's n squared possible combinations, including the A to A, B to B, C to C, as well as the A to B, B to A. So if 25% of those connections exist, then it is, or more, it is better to use, then you're in a dense graph category territory, and better use a array-based, a two-dimensional array. So let's go ahead and figure this out. So here we have 1,000 nodes and 1,200 edges. So we've got 1,200 edges and 1,000 nodes. How many possible edges are there? How many possible edges could have existed?
Isn't it n squared?
Yep. So what is n in this case?
1,000.
Right? What's n squared? Add on 3 more zeros and you got 1,000,000. So you've got, a million possible edges. We've got 1,200 edges. So is 1,200 25% of 1,000,000?
No.
No. So this is definitely a sparse graph. Here we have 100 nodes and 4,000 edges. 100 squared is what? I know we're all tired, but this one isn't that hard. What's 100 squared?
1,000.
It's 10,000. 10,000, right? Just simply double the number of zeros you've got. So 10,000, 4,000 edges out of 10,000. That's 40% of those possible edges. So this is definitely a good candidate. Here we have 1,000,000 possible edges again, and we're using 10,000. 10,000 out of 1,000,000 is 1%. So also not that great. And here we've got 10 nodes, which means 100 possible edges. And we've got 20 edges. So 20 out of 100, that's 20%. Like literally 20%. Which is not as, which is great, but not as great as B. So B is our answer here. All right. Binary tree is, so I like this one a lot. Okay. A binary tree, constructive nodes that are instances of the following class. Node, int, so we've got an integer value rather than an E. That's all that's different. They didn't go over generics for this class, I guess. That's okay. And it's got left and right node. So it's just a standard node, right? So consider this following method we have, which returns a node, and it's called mystery, and it takes in a node we call root. So it says, if root.right is null, if I don't have a right child, then I return myself. Otherwise, I return mystery calling my right child. So here we consult 3 supposedly tech-savvy consultants, and we get 3 opinions about what the method does when passed a reference to the root node, the top root of a binary search tree, or sorry, of a binary tree. Okay, and we get, and consultant 1 says it will return the last node visited by an in-order traversal. Consultant 2 says it is the last node visited by a post-order traversal. And consultant 3 says it returns the last node visited by a level order traversal, which again, as I mentioned just earlier in this class, he's talking about, this is what we call breadth first search in the context of trees. So last node returned by a breadth first search. So which of these opinions is correct for any tree? So let's go ahead and look at number 1. Number 1 says, I guess I don't have whiteboard, so I'm just going to have to use over here again. All right, number 1 says that's the last node visited in Inorder Traversal. So let's think about this. So we've got this. So let's go ahead and do this tree. And all we concern ourselves with is the right. There's no lefts in the method, right? So I'm just going to draw stuff. Okay. So in order traversal, we do our left subtree, then we do our south, then we do our right subtree. So here, what we're saying is, hey, if we don't have a right node, then return ourselves. Otherwise, call this, which says, hey, if I don't have a right node, return myself. Otherwise, call this. So this basically says, hey, call this on mystery on this node, which says call mystery on this node, which says call mystery on this node, which says call mystery on this node. And this node goes, I don't have a right subchild, so I guess I'm going to return myself. So we return this node over here, which is in fact the last node in a in-order traversal. So this method, what it's going to do is going to return the rightmost node in the tree, right? Basically saying if I can go further, if I can keep going right, then yes. Right. So suppose this guy didn't exist. We'd return this guy, and that's correct still, because we'd go, hey, okay, this guy says call, I'm going to handle my left subtree, then myself, then my right subtree. He's going to say handle my left subtree, then myself, then my right subtree. So opinion 1 is correct. It will return the last node visited by an in-order traversal. But let's check the others. Let's check and see, hey, last node visited in a post-order traversal. Well, post-order says I'm going to return the root. So I can actually kind of stop drawing now, because take a look at this. Post-order traversal. Well, post-order traversal says handle my left subtree, handle my right subtree, then handle myself. The last node in this is going to be the root. And the method says, hey, return this guy, which is not what happens. So number 2 is wrong, because we can create a counterexample very easily. But what about opinion number 3? Well, if we look at the graph we just drew over here, the last node visited by a level order traversal, which is what you would do in a heap, right? It says, hey, just go through here, and we're going to return, and we're going to visit them in this order. So that seems to work. But let's say we remove this node. Okay. So now level order traversal says 1, 2, 3, 4, 5, 6. So level order traversal would return this node, but our method would return this guy. So 3 is also a wrong opinion, because we found a counterexample. So the only opinion that's correct is A. Make sense to everybody? Does everybody follow that one?
Yep, makes sense.
Okay. Let's keep going. So with a poorly chosen hash function, it's possible to have a situation in which the search time in a hash table of n items goes to what? How bad can searching become if you have a bad hash function? How long would it take you to find an empty space or the thing you're looking for? Oven, right? You'd have to traverse everything in the array, in the hash function's underlying array to find an empty spot. It's not going to get any worse than that. All right, we did this for the first exam, so I'm going to skip that one. Okay. Let's go ahead and look at this one. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so it can be determined very quickly whether or not a given license plate is in the database. Speed of the response is very important. Efficient use of memory is also important, but not as important as the speed. So which of the following data structures is most appropriate for this? For storing these 1,800 license plate numbers for a very quick lookup. A sorted linked list, a sorted array with 1,800 entries, a hash table with using open addressing using respectively 1,800 entries, 3,600 entries, and 10,000 entries. All right, so let's talk about it. So first off, sorted linked list. Storage for that is O of n. In fact, all of these are O of n, but they are different degrees of O of n. Okay. Sorted linked list. How long does it take to find something in a sorted linked list? Suppose I'm trying to see, does the license plate 536 exist in, is that stored in this linked list? How long will that take? O of n. O of n. O of n, because you have to check every single thing. It being sorted means helps not at all. You can't do binary search on a very effectively on a sorted linked list, because you'd have to traverse to the middle, then you'd have to traverse to the middle of that, and then traverse to the middle of that. You can't just jump around where you can in a sorted array. Speaking of a sorted array with 1,800 entries, how long would that take to search? Given a number and a sorted array of numbers, how long does it take you to find your target?
Not long.
Not long. Specifically?
Is it log
Isn't it
n?
O of n?
It would be log n. Log n using binary search, right? You want to use binary search in this case. Make sense?
So when would you use O of n squared?
O of n squared for searching when you've done something horribly wrong.
Makes sense.
You don't do O of n squared for searching. Searching means let me find this item out of n items. The longest that will take is looking at all n items.
No, but like when would you actually use
O of n squared?
Would that be for something else other than
Yes, that's for other things like sorting or comparing all items to other items.
I had a question. So on the array, it takes a log n because we can access the index and all in a constant time, right? Compared to the linked list where you have to, even if you go in
Yeah,
the
you
middle.
can access a specific index in constant time. You can just get the value at an index in constant time, and then you have to do that a total of log n times maximum, right? Because you go to the middle, you say, is the number I'm looking for higher or lower, or is it equal to? And if it's not equal to, then you're going to be able to cut out half your search space. And since you're cutting it in half each time you do it, it's log of n. Make sense? Log base 2 of n specifically. Okay. Now let's take a look at this one. Hash table with an open addressing using 1,800 entries. Now hash tables in general, what is their lookup time? What is the big O for get and set for hash tables?
Big O.
Constant time?
Yep, constant time, big O1. Okay. However, that's highly dependent on memory usage and how much memory you have sacrificed. If you have 1,800 entries, right, how long does it take to find something in a completely 100% full hash table?
Over.
Oh, then.
O of n. And if that's confusing to you, consider the following metaphor. If you're trying to park your car in a parking garage, like you might do in the before times, before the pandemic. So if you're going somewhere trying to park your car in a parking garage, right? And you enter a parking garage and it says it has one space left. How long does it take you to find that space?
Well, in a garage it's pretty small, so.
A parking garage, parking deck.
Oh, like a lot.
Yeah. How long does it take if there's only one space left?
A long time.
Yeah, long time. Takes forever to find that parking space. Hash tables are kind of like that. To find an empty space or to find where you parked your car, so to speak, if you're looking to retrieve it, that can take forever. Okay, but now let's look at a hash table with open addressing using 3,600 entries, and we're going to extend this metaphor further. Okay, if you're entering a parking garage, right? There's 1,800 cars in it, but it's got capacity for 3,600 cars. So the lot is what percentage full?
Half.
50%. Right, 50%. 1,800 cars, 3,600 spots. It's half full at this point, right? Yeah, half. Sorry. So now, if you're trying to park your car and it's 50% full, how long does it take you to find an empty parking space?
Not long.
Truthfully, not very long at all.
Not at all. Yeah, it's half full. You're quick, in and out. Same thing happens for hash tables, right? It doesn't take long at all during an insertion to find an item. And if it doesn't take long for insertion, then it doesn't take long for retrieval. Okay. Now, here's the question. Let's extend this metaphor to number E. 1,800 cars in a 10,000 car sized parking lot. Doesn't take you long at all to find a parking space. In fact, you can find a parking space a little bit quicker than 3,600, right? Just a little bit quicker, but not significantly quicker. Not enough to make a difference, right? It's a negligible difference. But you're using 10,000, but you're using like, let's call it 5 times as much space as opposed to, well, let's just actually estimate. You're using about 3 times as much space as D. So in this case, D is our correct answer because C in this case, that's O of n time. Takes forever to find that one spot. Have to check every spot. D and E, you find it very quickly. Okay. This is something I go over briefly in the slides where Knuth has this formula from your it's from your textbook, basically saying, hey, if the hash table is this full, how long does it take? And here, this is basically saying, hey, it takes on average like 1.5 spots you got to look at. And here, you're on average looking at 1 spot, which on average isn't much of a difference. It's still constant time. So better to use D because we care about the speed of the response. They're both constant time, but efficient use of memory is also important. And this is way more efficient for our use of memory. Now, if we cared about our use of memory first, which would we want to use? Which of these 5? B.
Right.
B, because that's still very fast, log of n, but there's no overhead associated for using an array. All right. So a Huffman tree is constructed for a text document containing 5 characters. The E is the most frequent character, and the I is the next highest frequency. Which of the following could be a Huffman tree for this document? So first off, let's take a look at this. I is impossible. That is not a Huffman tree because one of the rules for Huffman trees is that you only get letters in the leaves. Make sense? And next, let's see, I and E are the most common documents, E and I are the most common, so they should take the least steps to get to. Here it takes 3 steps and 3 steps and 2 steps, 2 steps, 2 steps. So nope, because that takes the most to get to them. So over here, let's look at 2. Also, we can't rely on process of elimination because we have an E, none of these. So here, E is the most frequent. So that's filled. Next, I is the most frequent. But it's tied in terms of length for this. And that's feasibly possible. You might have something like, I don't know. Let's go ahead and say, hey, this has a frequency of this much or something like that. And this has a frequency of 1, 1. And this has a frequency of 2 and 2. Sorry, 1 and 1 and 3 and 3. So this gets a node of 2, then these get added together. Let's see. 1 and great. Now I have to reverse engineer. So let's go ahead and see how much I could add these guys together. So this guy by himself, that's fine. Let's see for this guy. We need to have the weights. So we need this to be added 1 and 5. That's fine. That adds up to 6. So 1 and 5, that adds up to 6. So next we would need to have before those. Let's go ahead. No, that's not going to make much of a difference. What about S and I? What values can we give those? So we can, it's got to be greater than 6, the value. 4 and 4, maybe? Except that wouldn't work. So 1 and 2 give us 3. And then, oh, yeah, 2 and 2. 1 and a bunch of 2s would do that. Because 1 and 2 would be 3 over here. 2 and 2 would be 4. The 2 and 2s would go first, so they'd make their own tree. Boom. So that would work. So the answer is D. I'm sorry, not D. It is B over here. B is the only one that will work or could possibly be a happen tree. Oops, didn't mean to hit stop sharing. All right, screen share again. An array of 7 integers is being sorted by the heap sort algorithm. Okay, so after the initial phase of the heap, which is of the algorithm, which is constructing the heapify stage, which is the following possible ordering for the array. So what are the 2 steps of the heap sort algorithm? Anyone? I understand you're all tired and completely burnt out and don't want to be here. I do. Does anybody want to volunteer the information or no?
Exit again, please.
What are the 2 steps for heap sort? The 2 broad steps for heap sort.
Is it to make everything into heaps and then to merge the heaps back together?
Close. It's to
Max heap.
Yeah, max heap. Turn it into a max heap, and then what? Broadly speaking.
So
don't have to get into the specifics.
Store the largest item in the root of the heap.
Yeah, that's what the max heap does. And what do you do with it then?
I don't know.
Sorry. You then start removing the item and putting it into the back of the array. Right? Since what you do is that since you've got a heap, you can keep removing the largest item from the heap, which is the top, reheapify it, and you'll end up with a sorted array after that. So
I like that term. Reheapify it.
Mm-hmm. So the phase of the algorithm, constructing the heap. So here we've constructed a max heap. So we're looking to see which of these is a max heap. That's what this question is asking a roundabout way. Which of these is turned into a max heap? So D is not a max heap because we've got to have the largest item, which is 85 in there. Now, also for it to be heap, we need it to be a heap all the way through. So 85's children are 78, and there's a formula for it, which you can look up. But for seven items, that's not too hard. 85's children are 78 and 45, and then 78's kids are these two guys. Sorry, these two guys, and 45's kids are these two guys. And basically, you got to say, hey, is the root larger than this? So let's look at, I'll draw out the first one for you. 85, 78, 45, 51, 53. So we're looking good so far. 47, and 49. So 45 is smaller than its kids, and that's a violation of the max heap property. Right? The parent has to be bigger, because the parent has to be bigger than both its children. So can't be A. What about B? We've got 85, 49, 78. Then you've got 49 is greater than these two, 45 and 47. 78 is bigger than those two. So that seems to work. 85 is bigger than these guys. 78 is bigger than those two guys. 45 is smaller, so it can't be C. And now 85, 51 is smaller than 53, so it can't be this. So our answer is B, because that's the only thing that actually gets us a heap, a max heap. 85, 49, 78, 45, 47. The formula is in the videos, and I don't want to spend 5 minutes trying to remember, banging my head trying to remember what it is, especially since I'm not going to be using that formula on the exam. So
I had a question. So in heap sort, you just do the max heap repeatedly, and the biggest element or the root gets set as the last element of the array? Or
what you do is that you remove the item from the heap and kind of silently move it into the back of the heap. Into the back of the array. So here,
That's the last element, right? Okay.
yeah, I did my videos on it. So, and the slides have good things. I just want to keep moving on to these questions because we do have a number of good questions, and we still have coding questions I want to talk about. So this is like what you would have had on your second exam. Binary search tree shown below was constructed by inserting a sequence of items into an empty tree. Which of the following sequences is not a binary search tree? So we'll not produce this. So 5, 3, 4, that would work. And then 9, 12, 7, 8, 6, 20. So adding these items in this order would produce this tree. 5, 9, 3, 7, then 6, then 8, then 4. We added 3, then 4, so that would work. Then 12, we added 9 before that, and then 20. 5, 9, 7, 8, 6, 12, 20, 3, 4. So that one works. 5, 9, 7, 3, 8, 12, 6, 4, 20. So what about E? 5, 9, 3, 6, then 7. So if we were to do this in that order, 5, 9, 3, 6, 7, 8. So we'd be getting a completely different tree structure in that case. So that's why for this question it is, right? Binary search tree below was constructed by inserting a sequence of items into an empty tree. Which of the input sequences will not produce this tree, right? They all would produce that tree except for the last one. All right, let's go ahead and look at this one. annotate. Suppose the keys in the standard row, middle row of a standard keyboard, A, S, D, F, G, H. Ooh, that was a big thunder. Are inserted into succession in an initially empty binary search tree. Draw a tree after all those have been added. So A, S is comes after A, then D, then F, G, H, so G, H, and then J, and then K, and then L. Very unbalanced tree here. Next question deals with 2-3 trees, but we didn't cover 2-3 trees, which is perfectly okay. Now, there's definitely going to be a question like this one on the exam. Definitely, always is. And I would know because I write this. We're given an empty hash table of size 7 that uses open addressing. So we're going to insert the following sequence of keys: 15, 17, 8, 23, 3, and 5. Insert these keys using the following approaches. If an overflow occurs, indicate the element that causes the overflow. H of X is our hash function is X mod 7 using linear programming. This one is X mod 7 using quadratic probing. So I will be right back. I'm going to get myself something to drink because I'm starting to feel a bit hoarse, but go ahead and think about this one and try to work on it. Many carbs. So like I said, this one is definitely on the final exam. I know because I wrote it, or something like this is on the final exam. So here, right, open addressing is the idea of if there's a conflict between where you're going to put your keys, use the next available space. Okay? And linear probing versus quadratic probing is our definition of what is the next available space. Linear programming or probing means literally let's find the next available space. Quadratic probing means let's go ahead and I'm going to look one away, then 1 squared away, then 2 squared away, then 3 squared away, then 4 squared away until I find an empty space. So let's go ahead and take a look. So our hash function is X, take X, our key, and mod by 7 to figure out where we're going to put it. So 15 mod 7 is what? What is 15 mod 7?
1.
Right, so we go ahead and put this guy 15 over here. 17 mod 7 is 3. We can just kind of logically extend that, right? This is 1, this is 2, 16 would be 2, 17 would be 3. So let's go ahead and do 8 mod 7. What is 8 mod 7? 1, right? 8 minus 1 is, 8 minus 7 is 1. So here we try to put it in here, but we can't. So what do?
Look for the next space, we just do.
Yep.
Linear problem.
Right. So I'm just going to draw an arrow to represent that we basically had to put that in. Okay. To indicate what causes an overflow. Okay. Next, we have to put in 23. The closest multiple to 7 of 23 is 21. Right. So 23 minus 21 is 2. So we want it, 23 really wants to go here. In fact, what I'm going to do to draw this, in fact, is I'm going to do 8 over here and just indicate that 8 really wanted to go here, but it couldn't. So 23 really wanted to go there. Nah, the way I had it was better. So 23 wanted to go here, but it couldn't. So we look for the next available space. That's taken. So we put 23 over here. Okay. 3 mod 7 is 3. So we wanted to put 3 here, but we couldn't. Look for the next available space. Look for the next available space. 3 goes over here. 5. The 5 index 5 is taken. So we look for the next available space. Goes over here. So 15, 8, 17, 23, 3, 5 is how things would get stored. Okay, now let's take a look at quadratic probing. Okay, how would that work? So our first moves would be the same. 15 goes over here. 15 mod 7 is 1. 17 mod 7 is 3. They end up over here. 8 mod 7 is 1. So we can't go there. So we look 1 squared away. 1 squared away is +1. So we look at 2. So we go over here at 8. All right. Now let's go ahead and look at 23. 23 wants to go where? It wants to go here, but it can't. So we look 1 squared away. We can't. So now we're going to look 2 squared away. So, and I'm going to look 2 squared away from our initial position, which is 4. So 1, 2, 3, 4. So we're going to plop it right over here. 23. Makes sense? So now let's try and do 3. 3 tried to go into this index, but it can't. So it's just plop. So we go to the next one, which is 1 squared away. And then 5. 5 mod 7, well, that ends up right over here. Boy, it's really coming down. All right. There are other functions besides this one. Besides just doing that, there's also bucket chaining, but you can also use double hashing, which we did not go over, but it is a possibility. Hold on a second. Annotate clear drawings. And double hashing, the way that works is that if you have a conflict, rather than trying to like look for the next available space, you use the second hash function instead. All right, graph algorithms. Okay, graph algorithms. Okay, so suppose we had graph algorithms, 15 points total. Perform a depth first traversal of the graph shown above, starting at vertex C. Okay. So we will go ahead and do that. And let's go with a violetish color. So we're going to start over here. Let's see. Okay. Select the smallest edge first when appropriate. In the space below, list the vertices in the order they appear. So depth first search means we travel down a branch as far as we can, and then we back up once we hit a dead end. So let's go ahead and take a look. I'm going to do this briskly, right? So what we're going to do is that we're going to go to C. We're going to start at C. And then we have got these 3 lines to go to. We've got 5, 22, and 30, right? Now it says in case of if we've got any kind of conflict as to which one we go and visit first, we choose the smallest edge first. So next we're going to go and visit B.
Hey, where's the box blanket?
The what?
I was making a pail.
You're making a what?
A pail.
A pile?
Yes, a pail made of blankets downstairs.
A pile made of blankets downstairs. Well, the big blanket's right there, right in front of you. Well, it's also not the safest thing to try to take those blankets down the stairs. So we can go ahead and do B. So we're at B. Let's look. The smallest edge is 5, but that takes us back to C, which we've already been to. 18, 20, 13, 17. So this is the smallest edge. So let's go to A next. So now we're at A. A's edges are 13 and 10, but we've been to B, so we don't want to backtrack over that edge. So let's go ahead and go to D. He found the fox blanket. Yay. C bad. All right, and so now D has 2 edges, 10 and 17. He's been to A. Just give me a second.
Go ahead and go downstairs. I'll bring this blanket and the other blanket.
The charm of working from home, right?
We have a giant pile of blankets downstairs, by the way.
Yeah, he's informed the class. It seemed like the utmost importance. Okay. So we went from C, we selected this edge, B, A, D. We go as deep into a route as we can. And now notice that we basically have hit a dead end because anywhere else we choose, we've already been. So here I'm going to go ahead and pop off D in our stack, so to speak, pop off A, pop off B. So we popped off A because that was also a dead end, and B, and now we're back to B. So let's not pop that off quite yet, but we've returned to there. And now B has, we're back at B. We have 5 edges from, B, 5, 13, 17, which we've already been to, but they also have the 18 and 20. So it says select the smallest edge first. So we're going to go to F. F is a dead end, C and B. So we pop off F. Then we're back to B. B has only one more edge to visit. Which goes to E. And pop off, and we're back to C. So C bad, FE. All right. Makes sense to everybody? Despite our interruptions? All right. For breadth first search, we look, again, if you're just trying to figure these out like from breadth this way, breadth first search is and depth first search are very easy because you can just kind of write down. So breadth first search basically says, hey, again, we're starting from C. It says, select the smallest edge first when appropriate. In the space below, list the vertices in the order they have visited. So let's list all the nodes that are distance. Let's mark all the nodes that are distance 1 away. 1, 1, and 1. Those are 1 step away from C. Right, 1, 1, and 1. And then 2 away. 1, 2, 1, 2. All right. So now it says what we want to do is we want to visit the smallest edge first when appropriate. So smallest edge 5, 22, and 30, right? 5, 22, and 30. 30 smallest is this one. So B goes first. Then E would be next. And then F, because those are our cheapest ones. He is screaming that he has hiccups. Well, more yelling and loudly proclaiming, not so much screaming. Okay, so we finished our one steps away. Now what about our 2 steps? So our 2 steps away are 13 and 17. So let's go ahead and do A and then D. C befad is our answer there. I'm going to do a more formal solution to the Dijkstra's algorithm because that one does necessitate a actual formal solution because Dijkstra's is kind of like that. So we want to find the shortest path from D to E, from here to here. List in the order they become known all the vertices which the shortest path is determined by in the process of solving the problem and the length of the shortest path. So, okay, so let's go ahead and we're going to zoom in, believe it or not, and we're going to go ahead and move this out of the way so that we have place to work. you have hiccups. Does anybody know a good solution for hiccups?
9/6
her.
of water.
Scare her.
Exactly.
You gotta scare them.
Gotta scare them. They say we
Peanut
gotta
butter.
peanut butter. He likes peanut butter. All right, so let's list our nodes: A, B, C, D, E, and F. Okay. So next, the important thing we need to know is the distance to the node and the previous. Okay. Oh, I'm sorry. I heard that. So those are our nodes. And then I will have a check mark over here for whether or not they are done. Done distance. Woo! Did that work? Do you still have hiccups? I thought you might. All right. So we are starting from node D according to this problem. So that will be done. Nothing else was. And so from D, we basically set up our initial distance
Hey,
of.
but that's a number 5 on the top.
It is a number 5 on the top. D, previous node is D.
And there's a number 10.
And there is a number 10. So
Which number is that?
this one, that's an 18. So now we've got laser. I need to teach class and they already know their numbers. So they, so over here, our initial distances are all infinity.
Don't have hiccups.
You still have hiccups. So, all right. So the way this works is that we look at D's neighbors. So sorry, we look at the edges coming out of D and we ask ourselves, what information does that give us? So D to A, let's look at and we always look at the shortest thing first. So D to A, this has a, so first off, what does this table tell us? It tells us this is the distance, this is how much it costs to get to this node from starting at D, okay, when our previous, and how we got there. So it costs infinity to get to everywhere. An infinite cost, meaning that you can't get there, right? So here, so from D to A, we know it costs 10. So it's 10 less than infinity? Yes, it is, hopefully. Okay, so we'll update this. So we update and say, hey, 10. Similarly, we're going to update 17. Or we're going to update D to B. And so now, in fact, we are done processing this one. So now at this point, we would actually check off D. Okay. So next, let's go ahead and look at the nodes A. So now we look through and we select the one with the shortest distance. So 10, 17, infinity. This is done. So we skip it. Infinity, infinity. Which of these numbers is smallest? That's A. So we're going to look at A now. A has 2 routes out of it, but this route is part of what we've already searched. So 13. 13, so 10 to 13. So here, it costs 13 to get to B. So the total cost to get to B, if we use this route, would be 23. Now, why 23? Because we're measuring the distance from D, and the distance to get to use this route over here, this edge, is 13 plus the amount it costs to get to A, which was 10. 13 plus 10. Is that smaller than 17? Is that a better price? No, it is not, so we don't add it. So we're done with that one. Now let's look at the remaining. B, C, E, F. So B is next. Now let's look at all these things. So first off, let's take a look. B to C is 5. To add that, we would have to add the cost to B, to get to B. So 17 plus 5, that is 22 total to get to C. Does that beat what we currently have? Yes, what we currently have is infinity. So put down. So now we're going to put down 22. What about B to F? That is 17 plus 18, which is 35. Okay, 35. And that beats infinity. And then B to E is 20 plus 17, which is 37. So we're done updating from B. Now let's look at which one of these is cheapest. 22, 37, and then 35. Next is C, because that is the next cheapest. Let's look at our routes. We've got 22 to get to E. So 22 plus 22, the cost to get to C is 22. The cost to get from C to E is 22. So 22 plus 22, that's 44. Is 44 less than what we currently have? No, it is not. What about F? 30 plus 22 is 30 plus 22 is 52. So no, that's not cheaper. So we're done with C. And then F is the next one, but both its routes lead back to the place we've been. And E is the next one, but routes have been lead back to the place we've been. So this is the output for Dijkstra's algorithm. And so our cost to get from D to E is 37. Okay. So Prim's algorithms, Kruskal, don't really want to. All right. So the part of this exam deals with binary. So a bit of programming before we go. Right. This part of the exam deals with binary trees that are constructed of nodes using this class. Okay, whatever, it doesn't really matter. The following Java method uses recursion to search for a tree whose root node is referred to the parameter by nit. If we find the key, it returns the reference to the corresponding data item. So this is just search without using generics, right? Root, key, and then basically we're doing a key value storage rather than just storing a single item. So here, given a key, find the object associated. In other words, a tree map. It works exactly the same as a tree, though. So using recursion, a public static object, node, key. If root is null, return null, right? This is just the standard algorithm, right? Everybody recognize this? So in the space below, we'll rewrite search so that it uses iteration rather than recursion. So I'll just boot up Visual Studio Code here. Preferences, settings. Let's go ahead and do a font size. Cascadia, and I want 24. And get yours true. And did it update to the Cascadia? Yes, it did. Very distinct fours in Cascadia, I think. Okay. And then not equal. I guess it didn't update completely. Work or no? Oh, I bet I don't have Cascadia. That's okay. Yeah. Issue with it. Whatever. My font choices are irrelevant at the moment. So let's go ahead and do this. Dot test dot Java save. Yeah, go ahead and install. I don't really need it though. Okay, I know. I know that I don't have any JRE installed right now. That's fine. I don't really need it for something like this. So public static, you use an object, search, and we're given a node root int key. So basically we want to use so if root equals null, return null in that case. Okay, otherwise what we need to do is say, hey, while I guess I'm going to do true because I don't know how long this loop is going to go for. While true, do the following. True. If root dot left. So let's go ahead and say, yeah, let's go ahead and do, yeah, this makes more sense. While root is equal to while root is not equal to null, return null if we get to the end. And now we just search for this in here, and we're going to return true if we manage to do so, if we manage to find it. So root, if key is less than root dot key, then that means go to left. If key equals root dot key, that means we found the item. And then finally, else if the key that we're looking for is bigger. So if it's the same, guess what? Just return root dot data was what they used. And then otherwise, if it's to the left, then root is equal to root dot left. Otherwise, go root is equal to root dot right. So, and that's really it. And if you find your key, great. And if you don't, you just throw it out. Okay, let's take a look at any remaining problems we have. So yeah, tomorrow we'll look on Thursday, we're going to look at mirror, which is one of my favorite problems. And then we're going to look at more coding problems from the other exams. This one had a lot of theory on it. Your final exam, around a bit more than 50 points are going to be on the theory, and the remainder are on coding. So keep that in mind. All right, stop share.